Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1876 publication by Georg Cantor, titled On the Property of the Collection of All Real Algebraic Numbers, represents a pivotal moment in the history of mathematical thought, a work whose slender page count belies the profound depth of its consequences. It is a paper that achieves its revolutionary aims with an almost deceptive simplicity, moving with quiet confidence from a seemingly modest observation about ordering equations to a conclusion that fundamentally reconfigures our understanding of the number line and the nature of infinity itself. This essay will provide a direct and rigorous evaluation of the internal claims, mechanisms, and logical architecture of this seminal work. We will proceed section by section, examining the specific arguments Cantor presents, assessing the methodology he employs, and deriving an understanding of the paper's importance from the cogency of its internal structure, a structure that builds with inexorable force toward one of mathematics' most elegant existence proofs. The scope of this analysis is focused squarely on the text itself, treating the paper as a self-contained intellectual artifact whose claims merit close and sustained scrutiny to fully appreciate the originality of its contribution and the foundation it laid for the development of set theory. Section 1, establishing the innumerability of the real algebraic numbers. The initial section of Cantor's paper embarks on a task both foundational and essential for his ultimate argument to demonstrate that the collection of all real algebraic numbers possesses the property of countability. An algebraic number is defined as any real number that serves as a root of a polynomial equation with integer coefficients. Cantor's central claim in this section is that this entire, seemingly vast collection can be arranged into a single, definite, infinite sequence. The mechanism for this proof is an ingenious organizational principle based on what he terms the height of the defining polynomial. He considers a polynomial equation of degree n of the form a sub 0 times x to the power of n plus a sub 1 times x to the power of n minus 1, and so on down to a sub n equals 0, where all coefficients are integers and the leading coefficient, a sub 0, is positive. He then defines a positive integer he calls n, which is the sum of the degree n and the absolute values of all the coefficients from a sub 0 to a sub n. The critical insight here is that for any given positive integer value of this height n, there exists solely a finite number of such polynomial equations. This is because the degree n and all the integer coefficients are bounded by n, with a finite pool of available integers for the coefficients and a maximum degree. The number of possible combinations is necessarily finite. Having established this, Cantor lays out his enumeration procedure. He proposes to order these equations first according to their height n, starting with the lowest possible value, which is 2. For all equations sharing the same height n, he stipulates they can be ordered by some other consistent, albeit arbitrary, rule, for instance, by the magnitude of their coefficients. Since each polynomial equation has a finite number of real roots, one can then list these roots in their natural order of magnitude for each equation in the sequence. By proceeding through the ordered list of all such polynomial equations and listing their real roots in turn, one constructs a single, comprehensive sequence, omega sub 1, omega sub 2, omega sub 3, so on, that incorporates every real algebraic. The evaluation of this claim reveals its quiet brilliance. The methodology is entirely constructive and systematic. Cantor provides a concrete procedure that, in principle, allows for the assignment of a unique natural number to any given real algebraic number. The argument's validity rests on the verifiable finitude of equations for any given height n. The potential for a single number to be a root of multiple equations is acknowledged and presents no obstacle. The number is simply included in the sequence upon its first appearance. The claim that the set of all real algebraic numbers is countable, or enumerable, is thus rigorously substantiated. This result was in itself a significant contribution to number theory, Establishing a fundamental characteristic of this important class of numbers, it provided a formal structure to a set that might otherwise have been perceived as intractably dense and complex. The intellectual elegance of the height function is that it transforms a problem of infinite complexity into a series of finite, manageable steps, a technique that demonstrates Cantor's emerging mastery of handling infinite collections. This section, therefore, functions as a masterfully executed foundational step, providing the first of two pillars upon which his final conclusion will rest. Its internal logic is unassailable, and its claim is demonstrated with a clarity that leaves little room for Section 2. The construction of an unenumerated real number. The second part of the paper marks a transition from classification to construction, although it is a construction of a most peculiar and abstract kind. Here, Cantor advances a claim of immense power for any given infinite sequence of distinct real numbers. It is possible to define a real number that is absent from that sequence. This is the conceptual core of the paper, the engine that will drive it toward its revolutionary conclusion. The argument is a masterpiece of logical precision, relying on the properties of nested intervals and the completeness of the real number line. Cantor begins by positing an arbitrary infinite sequence of distinct real numbers, which he denotes omega sub 1, omega sub 2, omega sub 3, and so forth, spanning across a given interval from A to B. The objective is to produce a number, which he calls eta, within this interval from A to B, such that eta is distinct from every member of the omega sequence. The procedure unfolds iteratively. Cantor first identifies the two numbers in the omega sequence with the smallest indices that lie strictly between and B. Let these be omega sub k and omega sub l, with k being less than l. He then defines a new, smaller, closed interval for a prime to B prime that is situated entirely within the original interval from A to B but is chosen specifically to lie between omega sub k and omega sub l. This new interval, by its very construction, excludes these first two members of the sequence found within the initial boundaries. The process is then repeated. Within the new interval from A prime to B prime, he finds the two members of the omega sequence with the next smallest indices, say omega sub m and omega sub n, and defines a yet smaller interval from A double prime to B double prime that lies between them. This third interval is thus nested within the second and is guaranteed to exclude omega sub m and omega sub n. This iterative definition continues indefinitely. At each stage, a new closed interval is created that is a proper subset of the previous one, and which is explicitly constructed to omit certain members of the omega sequence. The evaluation of this mechanism reveals its profound reliance on the structure of the real continuum. The result of this infinite process is a sequence of nested closed intervals whose lengths converge towards zero by a fundamental principle of real analysis, known today as the nested interval theorem. The intersection of such a sequence at intervals contains precisely one point. Cantor designates this uniquely determined limit point as eta. The central claim is that this number eta cannot be any of the numbers in the original omega sequence. The proof of this claim follows directly from the construction. For any given number in the sequence, say omega sub p, it must eventually be considered in the interval-defining process. At some stage, an interval will be constructed specifically to exclude omega sub p. Since all subsequent intervals are contained within this one, the final limit point eta must also lie within this interval, and therefore eta must be a different point from omega sub p. This holds true for every single member of the omega sequence. Thus, the constructed point eta occupies a position on the real line distinct from every member of the proposed enumeration. This argument is a sterling example of an indirect existence proof. It establishes that a number with a specific property of being outside a given enumeration must exist, without providing a method to calculate its decimal expansion. The claim's validity hinges on the completeness of the real numbers, the very property that guarantees a limit point for the sequence of nested intervals. The reception of such non-constructive methods would become a point of significant philosophical debate in mathematics, most famously with the objections of Leopold Kronecker who held that mathematical objects only exist if they can be explicitly constructed from a purely logical perspective within the framework of classical mathematics. However, Cantor's reasoning is flawless. He demonstrates that any attempt to list all real numbers in a sequence is doomed to failure, as a number can always be found that is missing from the list. The property he has uncovered is the uncountability of any interval of real number by extension, the uncountability of the entire set of real Section 3. The synthesis of enumerability and non-enumerability to prove transcendence, the final, decisive step in Cantor's 1876 paper, is a synthesis of the conclusions reached in the preceding 2 sections. This part of the work contains no new complex machinery. Its power is purely logical, deriving a startling conclusion from the juxtaposition of his 2 primary claims. The argument is brief, elegant, and world-changing. It serves to provide the first of a rigorous proof for the existence of transcendental numbers, which are real numbers that are absent from the set of algebraic numbers. Prior to Cantor, the existence of such numbers was suspected, and Joseph Liouville had in 1844 even constructed a specific example of one. Cantor's achievement was of a different order entirely, for he proved that such numbers must exist without constructing a single one. His proof, in fact, implies that they exist in an abundance that dwarfs the full collection of algebraic The synthesis unfolds with an elegant syllogism. From Section 1, we have the rigorously established claim that the collection of all real algebraic numbers is innumerable. This means it is possible to arrange them all into a single, definite infinite sequence of the type omega sub 1, omega sub 2, omega sub 3, and so on. This is the first premise. From Section 2, we have the equally rigorous claim that for any such infinite sequence of distinct real numbers, there necessarily exists a real number, the point eta, which is absent from that sequence. This is the second premise. Cantor then applies the general result of the second section to the specific sequence established in the first. He considers the complete, exhaustive enumeration of all real algebraic numbers. The argument from Section 2 guarantees the existence of a real number that is located outside this comprehensive list. The conclusion is inescapable. This number, whose existence is logically necessary, is a real number that, by its very nature, fails to appear in the full sequence of all real algebraic numbers. It is therefore a real number that is non-algebraic. The name for such a number is transcendental. Cantor's argument thus culminates in the affirmation that the set of transcendental numbers is populated. His proof does more than this. It establishes that the set is non-empty. It implies that in any interval of the real number line, after one lists all the countable algebraic numbers within it, an uncountable infinity of transcendental numbers remains. This result offers a first, dizzying glimpse into the new world of transfinite arithmetic, where different orders of infinity exist. The irony, a piece of subtle academic humour perhaps lost on his more dogmatic contemporaries. Algebraic numbers, which include all the familiar integers and rational numbers, constitute a vanishingly small fraction of the real number line. They appear to so densely populate. Evaluating this synthesis requires an appreciation for its abstract power. The argument's beauty lies in its generality and its independence from the messy particulars of constructing specific numbers. It is a pure existence proof that changed the prevailing philosophical orientation of mathematics. The focus shifted from the properties of individual numbers to the structural properties of entire infinite sets. The claim regarding the existence of transcendentals is a direct and unassailable consequence of the 2 prior claims, each of which was demonstrated with meticulous care. The paper as a whole functions like a perfectly calibrated logical instrument, with each section serving a precise purpose in service of the final conclusion. Its internal coherence is absolute. The work demonstrates that the set of real numbers and the set of algebraic numbers, while both infinite or infinites of a fundamentally different magnitude or power, a concept that Cantor would spend the rest of his career Conclusion. In conclusion, Georg Cantor's 1876 paper on a property of the collection of all real algebraic numbers stands as a monument of intellectual economy and profound insight. The systematic evaluation of its internal claims reveals a logical structure of exceptional clarity and force. The first section's claim of the enumerability of the algebraic numbers is substantiated through the clever and robust mechanism of the height function, providing a crucial and significant result in its own right. The second section's argument for the existence of an unenumerated number, proven via the elegant construction of nested intervals, is a testament to the power of abstract reasoning and a deep understanding of the properties of the real continuum. The final synthesis of these two claims provides an irrefutable, if non-constructive, proof for the existence of transcendental numbers, thereby resolving a major open question in mathematics. The enduring significance of the work, assessed through the direct analysis of its components, lies less in the specific result about transcendental numbers and more in the revolutionary methodology it introduced. Cantor's paper operationalized the comparison of infinite sets, demonstrating that infinities possess a rich and varied structure. By proving that the continuum of real numbers is of a higher order of infinity than the set of algebraic numbers, he opened the door to transfinite set theory and forever altered the landscape of pure mathematics. The paper's claims, from its initial ordering principle to its final logical leap, cohere into a unified and powerful argument that is as sound today as it was innovative in 1876, a testament to a mind beginning to navigate the uncharted territories of the infinite.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.